Welcome viewers. In this video we'll see the Amperes law definition followed by applications of Amperes law. First we'll see the statement of Amperes law. The statement is the line integral of tangential component of magnetic field intensity H around a closed path is exactly equal to the current enclosed by that path. Suppose if conductor is available, current is flowing through the conductor, the magnetic field is produced in and around the conductor. That magnetic field is equal to amount of current enclosed in the conductor. That is the statement given by the Amperes law. Integral H dot dl equal to I. So when a current is flowing through a conductor, the magnetic field is produced. So the magnetic field is equal to amount of current enclosed in that path. The closed path is required while applying the Amperes law. So in the closed path, the entire magnetic field intensity is equal to current flowing through that closed path, right? So it's a statement given by Ampere law is integral H dot dl equal to I. Now we'll see the applications of Ampere's law. There are three applications available. We'll see one by one. The first application is magnetic field intensity due to long wire. The magnetic field intensity due to finite wire is available in separate video. This is long wire, right? Finite wire means the length is defined, but here the length is not defined. It's a long wire. Now consider the circular loop with radius d meter, right? So refer this diagram. We are considering one circular loop with diameter d. So this is nothing but the conductor. The conductor, current I is flowing through the conductor. So due to this current flow, the magnetic field is produced in and around the conductor. In order to apply the Ampere's law, we construct one circular current loop with radius d meter. According to Ampere's law, what is that? Integral H dot dl equal to I. So the H is constant, so integral dl equal to I. What is integral dl? Integral dl is nothing but perimeter of this circular current loop. For example, this circumference of the circular current loop is nothing but a integral dl. That is integral dl is L. L is nothing but length. Length is nothing but circumference. So that is equal to 2 pi d. Right? So integral H dot dl equal to I. So H into integral dl equal to I. Integral dl is L. L is nothing but perimeter. That is nothing but 2 pi d. Right? So we can replace this integral dl with 2 pi d. So H dot 2 pi d equal to I. So H equal to I divided by 2 pi d. Right? So this is the magnetic field intensity due to a long wire. So this magnetic field intensity depends upon two parameters. What is the current flowing through the conductor and the circular current loop, the radius of the circular current loop d, right? It is inversely proportional. Current is directly proportional, d is inversely proportional, right? So the final expression is H equal to I divided by 2 pi d. Now we'll see the second application. The second application is magnetic field intensity due to the solenoid. Due to long solenoid. This is also a long solenoid. Right? The magnetic field intensity due to normal solenoid available in a separate video. This is application of Ampere's law under that magnetic field intensity due to a long solenoid. You know that the solenoid is an electromagnet. It's an electromagnet. It is formed by winding few turns over a iron rod. Right? One iron rod is there over which if the coils are winded, when the current is flowing through the coil, it becomes electromagnet. So that is nothing but solenoid. Solenoid is a over a iron rod. The windings are available. When the supply is given, it becomes electromagnet. Now consider the solenoid with length L as shown in the diagram. Right? We are going to consider the solenoid with the length L meters. So this is the solenoid. This is iron rod over which the coils are winded. When the supply given, it become electromagnet. The length of the solenoid is L meters. In order to apply Ampere's law, what we need is closed path is needed. When closed path is needed, then only we can apply the Ampere's law. So this closed path is A, B, C, D, A. So this path AB is available inside the solenoid, the CD available outside the solenoid. So that we can analyze what is the magnetic field intensity inside as well as outside of the solenoid. Right? So this is the iron rod over which the coils are available. When the supply given, it become electromagnet. The length of the solenoid is L meter. In order to apply the Ampere's law, we construct one closed loop AB, CD, A is such that AB available inside the solenoid, CD available outside the solenoid. Now we'll see what is the magnetic field intensity inside and outside the solenoid. Let us consider H1 is the magnetic field intensity available inside the solenoid. H1. H2 is the magnetic field intensity outside the solenoid. Right? We assume that we consider H1 is the magnetic field intensity inside the solenoid. H2 is the magnetic field intensity outside the solenoid. Now we can apply the Ampere's law. Apply Ampere's law to the closed path A, B, C, D, A. We'll see what is the Ampere's law. Integral H dot dl equal to I. We need to see what is the work done along this AB, BC, CD and DA. For all four paths, what is the work done? We need to analyze. The work done along AB is H1 into L, because the magnetic field intensity inside the solenoid is H1. So H1 into L, integral H dot dl. So H1 into L. The work done along CD outside is H2L. We assume that magnetic field intensity outside the solenoid is H2, right? So inside the solenoid H1, outside the solenoid H2. The work done along the path AB that is available inside is H1L. Work done along CD that is available outside is H2L. Then what is the work done along BC and DA? So work done along BC and DA is 0. Why? The magnetic field intensity and DL are perpendicular. Both are perpendicular to each other. So the magnetic field intensity in the path BC as well as DA is 0. Only the magnetic field intensity, the work done available along AB and CD. BC and DA is 0 because of perpendicular. So due to that, what we have, H1L plus H2L equal to N into I. The work done inside the solenoid, work done outside the solenoid, that is equal to current. Here N number of turns available, so that it is multiplied by Ni. So H1L plus H2L equal to Ni. Right. Now we'll see what is H1, what is H2. So the entire magnetic flux is flowing through the coil of the solenoid. Right, when the current is passed through the solenoid, the entire current is flowing through the solenoid. That is, the flux outside the solenoid is 0. We assume that entire flux is available only inside the solenoid. Outside the solenoid, the flux is 0. That is, H2 is 0. So that the flux flowing through the least reluctance path. So it will follow the least reluctant path that is available in the iron rod. Outside, the iron rod is not there. So outside, the magnetic field intensity is 0. Why? It follows the least reluctance path. So only H1 is available. H1L equal to Ni. This term become 0. So H1L equal to Ni means from that H1 equal to Ni divided by L. So here also the magnetic field intensity depends upon what is the current flowing through the coil, what is the number of turns in the coil, and what is the length of the solenoid. So these three parameters will decide the magnetic field intensity of long solenoid. H1 equal to Ni divided by L. Now we'll see the third application. The third application is magnetic field intensity due to infinite current sheet. One infinite current sheet is available. In that we are going to find what is the electric field intensity. So before that we see what is current density. An infinite current sheet can be assumed to be formed by several sheets in parallel. Infinite current sheet means there are n number of sheets available that are placed in a parallel, like a notebook. Each and every paper is the parallel is the infinite current sheet. Like that, n number of papers are arranged in a parallel. So linear current density or sheet current density is nothing but current per unit length. Always the density means either area, volume or length will be referred. Here we are referring the length of the current sheet, right? So linear current density is nothing but current per unit length, that is K equal to I divided by delta L, ampere per meter. So I equal to K into delta L. So you can cross multiply this so that I equal to K into delta L. So that can be used in the derivation, right? So we have infinite current sheet is available. We assume that there are n number of sheets available in parallel. So the current density is nothing but current per unit length, ampere per meter. From that we can find current equal to the current density into delta L. I equal to K into delta L. Now we'll see the diagram. So this is nothing but a infinite current sheet. The magnetic field available is H. The infinite current sheet is available. In order to apply Ampere's law, what we need? One closed path. A, B, C, D, A. We construct one closed path A, B, C, D, A in the infinite current sheet. The path is available inside, the path is available outside. The closed path, part is available inside, part available outside. The length of the closed loop is delta L. Right. So an infinite current sheet is shown in diagram. This is the infinite current sheet. Let us consider the rectangular path A, B, C, D, A. A, B, C, D, A. Now we are going to apply the Ampere's law to the closed path A, B, C, D, A. So while applying Ampere's law, definitely we need one closed path. Right. So according to Ampere's law, integral H dot dl equal to I for a closed path A, B, C, D, A. Right. For a closed path A, B, C, D, A. Now that is split into four parts: A, B, B, C, C, D and D, A. So integral H dot dl for a path A, B. Integral H dot dl for a path B, C. Integral H dot dl for a path C, D. Integral H dot dl for a path dA, that is equal to I. So what is the work done along these four different paths? The work done along BC and DA is 0 because the magnetic field intensity is 0 in normal direction. In the previous derivation solenoid also we did like that. For BC and DA it is normal direction, so the magnetic field intensity is 0 for BC as well as DA. What about AB and CD? The magnetic field available in AB and CD. See this, for AB the magnetic field intensity will be H. Similarly for CD the magnetic field intensity will be H. Only for BC and DA it becomes 0 because of normal. Right. So now we can apply this. For a path AB, H into DL. There is no H1, H2. We assumed only H into DL. For BC it is 0 due to normal direction. And CD again H dot DL outside. Then this DA also 0. That is equal to I. I can be replaced as K into DL. That is current density. From the current density we already discussed. Right. So H DL plus H into DL. So it becomes 2H into DL. That is equal to K into DL. The DL got cancelled. 2H equal to K. From that H equal to K divided by 2. So magnetic field intensity due to finite current sheet, the final expression is H equal to K by 2. So this is depends only on the current density of the current sheet. Right? H equal to K divided by 2. So in this video we discuss the Ampere's law statement followed by applications of Ampere's law. 3 different applications we discuss. infinite long wire, long solenoid and infinite current seed. Thank you.